Good evening everyone, good evening. I welcome you all again to Catalysis by Vedantu. Hoping that you guys are doing great, having the good time. Well people, you can let me know in the chat box if I'm audible and visible to everyone. Hello Shreyas, hi Manisha. Hello NEET aspirant, hello Nirmal, hi Rahul, hi Priyal. Welcome everyone, welcome back to Catalysis by Vedantu. Just let me know in the chat box if I'm audible and visible to everyone so that we can start the session directly, yeah? Hello Marvin, hi Bhumika, hello Priyal. Hello sir, hi VSG, welcome everyone, welcome back. Just give me some green signal from the chat box so that I'll get to know whether I'm audible and visible to you guys or not. Yes Harish, it'll be sufficient, yes absolutely. Wonderful guys, great. Perfect. Just give me a second, we'll be starting. Alright, so people, as you all must be knowing, tonight we are going to start a session, right? And in this session, basically, we are going to do the set of questions from the general organic chemistry. And I'm sure by solving these questions, your entire general organic chemistry will be getting revised, yeah? Okay, so before starting the session, for the ones who do not know me, let me introduce myself. My name is Wassim Sir and I'm your chemistry master teacher right here. Okay. Yes, Kasa, Mahesh, all in one video. Yes, absolutely. The ones who have not liked the video yet, please do like the video, share the video with your friends and do not forget to subscribe to the channel as well. So people, you can let me know in the chat box if you guys are super duper excited about this session. Yeah. Just let me know in the chat box if you guys are super duper excited about it so that we can start the session without wasting a lot of time. Yeah. Just let me know in the chat box. Let me see the josh of the session first. Yeah? Wonderful. Perfect, guys. Perfect. Perfect. So I'm sure you guys are ready with your pen and paper because it's you who is going to solve the questions right here. Yeah? Okay? So let's get started. Let's get started with the first question, which is on your screen. Okay? I'm exactly going to start from the basics. Right here. Well, people, as you can see this question, arrange the following species in the stability order, right? Basically, everywhere, these are basically 4 questions right here, right? If you look at the questions, have a look. I'm given with some charged species over here, and I need to check the stability of the charge over here, right? So basically, I'm supposed to check in which of the 4 positive charge is more stable. Similarly, in the second question, I need to check among these 4, where is the negative charge the most stable, right? Similarly, where is the negative charge stable among these 2? Similarly, where is the negative charge stable among these 4, right? Now, people, there is a rule, there is a concept which I want you guys to take a note of first of all, yeah? Remember the point number 1, a very important point. Whenever we need to compare the stability of charges on the elements which belong to the same period. Whenever I need to check the stability of the charges and the elements are belonging to the same period, for example, at that time we compare the stability of the charges by the electronegativity of the elements, right? By the electronegativity of the elements. Point number 1. Again, I'm telling you, whenever we need to compare the stability of the charges on the elements which belong to the same period, at that time we talk in terms of electronegativity, right? Remember, negative charge on more electronegative element is considered to be stable, yeah? And negative charge on less electronegative element is considered to be unstable, right? Similarly, positive charge on the less electronegative element is considered to be stable, and positive charge on the more electronegative element is considered to be less stable, right? These are the things which you need to take a note of. Point number 1. Whenever we need to compare the stability of the charges on the elements belonging to the same period, at that time we compare the stabilities in terms of the electronegativity, yeah? Negative charge on more electronegative element is considered to be stable, negative charge on less electronegative element is considered to be less stable. Similarly, positive charge on less electronegative element is considered to be stable, and the positive charge on more electronegative element is considered to be less stable. Okay. Well, people, if you can have a look on the first question right here. Carbon, nitrogen, oxygen, fluorine. All these elements, they belong to the same period, right? All these elements, they belong to the same period, right? So I need to compare the stability of the positive charge on these elements, right? Since all these elements, they are belonging to the same period, so I'll be comparing the stability on the basis of what? On the basis of electronegativity, right? And we know positive charge on less electronegative element is considered to be stable, right? Which one is the least electronegative among all? Carbon is the least electronegative among all. So positive charge on carbon will be considered to be as the maximum stable, followed by nitrogen, followed by oxygen, followed by fluorine. This is going to be the order, yeah? Similarly, if you look at the second question, have a look. Over here, you have got the negative charge on carbon, negative charge on nitrogen, negative charge on oxygen, and negative charge on fluorine. First of all, have a look, understand properly. See guys, first of all, properly understand this carbon, nitrogen, oxygen, and fluorine, they belong to the same period, right? And whenever we need to compare the stability of the charges on the elements which belong to the same period, at that time, what do we check? At that time, we talk in terms of electronegativity, right? And negative charge is more stable on more electronegative element, right? So negative charge will be more stable on fluorine. So this is going to be simply the stability order of these negative charges over here, yeah? As simple as that, right? Similarly, if you look at the third question, right? Before solving the third question, let me give you one more concept over here. Understand properly. Understand properly what I'm going to check. Remember, whenever we need to compare the stability of the charges on the elements which belong to the same group, whenever we need to compare the stability of the charges on the elements which belong to the same group, at that time, we talk in terms of volume charge density, right? At that time, we talk in terms of volume charge density. Now, the point is what this volume charge density is all about. Volume charge density is simply the ratio of charge present on the species divided by size of the species. Charge present on the species divided by size on the species. As simple as that, okay? See guys, remember, more the size of the species, less is going to be the volume charge density on it, right? Similarly, less the size of the species, of the charged species, I can say more will be the volume charge density, because both are inversely proportional to each other, right? Okay, and remember, volume charge density is inversely proportional to stability of the charge. Okay, volume charge density is inversely proportional to stability. Remember this, okay? Now we will have a look. Sulfur and chlorine, do they belong to same group or same period? Sulfur and chlorine, they belong to the same period, we know it, right? And whenever we need to compare the stability of charges on the elements belonging to the same period, at that time we talk in terms of electronegativity, we know it, right? Sulfur and chlorine, which one is more electronegative over here? You'll simply say chlorine is more electronegative, chlorine is more electronegative than that of sulfur, and negative charge is more stable on more electronegative element. As simple as that, right? So this is going to be the stability order of the negative charge over here. Yes. Similarly, guys, let's have a look on the last question over here. Over here, we have got negative charge on oxygen, negative charge on sulfur, negative charge on Se, negative charge on Te. Do these elements belong to same group or same period? Oxygen, sulfur, silurium, and tellurium, they belong to the same group, right? And whenever we need to compare the stability of the charges on the elements belonging to the same group, at that time we talk in terms of volume charge density, right? Now people, we know volume charge density is inversely proportional to stability, right? And volume charge density is basically the charge present on the species divided by size of the species, correct? Now, among oxygen, sulfur, Se and Te, which one is having the minimum size? Or which one is having the maximum size? Oxygen, sulfur, Se and Te. This Te has got the maximum size. If Te has got the maximum size, it has got the least volume charge density. If this Se has got the least volume charge density, that means its stability is going to be more. So I'll say negative charge will be more stable on this, followed by this one, right? This is going to be the order. Yeah. Just let me know in the chat box if it is clear to everyone. Let me know in the chat box, give me some thumbs ups in the chat box so that I'll get to know whether it's clear to you or not. Let me know in the chat box fast. So people, one thing which you need to remember, what is that? Whenever you need to compare the stability of the charges on the elements which belong to the same period, at that time you'll be checking it on the basis of electronegativity, right? Similarly, whenever you need to compare the stability of the charges on the elements which belong to the same group, at that time we talk in terms of volume charge density. Less the volume charge density, more the stability. That's it. That's it. There is no exception in this, okay? I'm sure it's clear to everyone, yeah? Perfect. Wonderful. So this one is also done. Let's move on to a few more questions, yeah? Let's move on to a few more questions. So this one is done. Let's move on to one more question. Look here, guys. Understand properly. We have got, again, these are 4 more questions and you guys will be giving it a try and you guys will be letting me know the answer by using the same concept, by applying the same concept which I told you right now, yeah? Understand properly, how will I be solving these questions? First of all, we have got negative charge on nitrogen, negative charge on phosphorus, negative charge on arsenic, negative charge on antimony, right? Nitrogen, P, As and Sb. Do these elements, do they belong to same group or same period? These elements, nitrogen, phosphorus, arsenic, antimony, they belong to the same group. They belong to the same group, absolutely, right? And whenever we need to compare the stability of the charges belonging to the same group, at that time, we use the concept of volume charge density, right? And volume charge density is inversely proportional to size, we know it, right? Volume charge density is inversely proportional to size, correct? Now we will have a look. Which one is having maximum size among the all? This SB will be having maximum size. If SB has got the maximum size, so it will be having least volume charge density. So if it has least volume charge density, we know volume charge density is inversely proportional to stability, right? If volume charge density over here is least, that means stability will be the maximum. So what is going to be the stability order? This is going to be the stability order, as simple as that, yeah? Right? Wonderful. Let's move on to one more question. Have a look. Over here we have got negative charge on oxygen, negative charge on sulfur. Oxygen and sulfur, do they belong to same period or same group? They belong to same group, right? And whenever we need to compare the stability of the charges on the elements belonging to the same group, at that time we use the concept of volume charge density, right? Since sulfur comes after oxygen, that means sulfur has got more size. If sulfur has more size, that means it has got less volume charge density. Less volume charge density means more stability. So over here in this one, negative charge is more stable, yeah? Okay, now people, right here you have got the positive charge on this carbon, positive charge on this carbon, positive charge on this carbon, right? It's a single bonded carbon right here, it's a double bonded carbon, it's a triple bonded carbon, right? Triple bonded carbon is considered to be more electronegative than that of double bonded carbon, than that of this single bonded carbon, as you all must be knowing, right? Okay, due to S character, yeah? So can you clearly let me know which carbon is maximum electronegative among all? This carbon is maximum electronegative among all, right? And positive charge on more electronegative element is considered to be least stable, right? Positive charge on more electronegative element is considered as the least stable, right? So over here positive charge will be least stable, so the stability order of the positive charge is going to be this one, yeah? As simple as that, right? 1, 2, 3, correct? Similarly, let's take a look on the 4th question. Have a look. Again, you have got a single bonded carbon over here. This is double bonded carbon. This is triple bonded carbon, right? Which one has got more electronegativity? Which carbon is more electronegative among all? This carbon is more electronegative. If this carbon is more electronegative, we know negative charge is more stable on more electronegative element. So negative charge will be more stable on this carbon, right? So this is going to be the stability order, right? So just let me know in the chat box if it is clear till here so that I can move on to the next one. Exactly, guys. All of you are right. All of you are right. Wonderful. Let me know in the chat box if it is clear to everyone so that I can move on to the next one. Wonderful. Wonderful, guys. Let's move on to few more questions, yeah? Okay, these are the stability orders which I've told you right now. And people, at the same time, you'll be getting this PDF on the Telegram group. Okay, so stay updated till the end. Well, we have got one more question right here, and I'm sure you all can easily solve this question. Okay, see guys. Just give me a second. Okay, understand. Over here we have got a 3-membered ring. Right here we have got 4-membered ring, 5-membered ring, 6-membered ring. Okay. Remember, this carbon of the 3-membered ring is considered as the maximum electronegative because this ring is under maximum strain, and that ring which will be under maximum strain, its element over here, which is carbon, it's going to be maximum electronegative, right? Okay, remember that ring which will be under maximum angle strain, you can say that ring which will be having maximum angle strain. Okay, that ring is going to be considered as the maximum electronegative, right? So if I consider these carbon atoms, which carry the negative charge, if I ask you which carbon is the maximum electronegative among all, see guys, the first ring, it is under maximum strain, so this carbon is going to be maximum electronegative, right? And negative charge is more stable on more electronegative element, so this is going to be the stability order right here. Yeah, as simple as that. Similarly, if you look at the next case, have a look. Again, we have got a 3-membered ring over here. Okay, this is a 4-membered ring, this is a 5-membered ring, this is a 6-membered ring. Where is the angle strain more? Angle strain is more in the 3-membered ring. So the carbon right here is considered to be more electronegative, right? And positive charge on more electronegative element is considered to be least stable. So what is going to be the stability order? This is going to be the stability order, as simple as that, yeah? Right? Let me know in the chat box if it's clear till here. Let me know fast. Mohammed Rahil, we are basically comparing the stability of the charges, okay? We are comparing the stability of the charges. So do not take into consideration the electronic configuration, yeah? Perfecto, guys, wonderful. All right, let's move on to a few more questions, yeah? Let's move on to a few more questions. Arrange the following in the acidic strength order. You need to arrange the following on the basis of their acidic strength. And I'm sure you all can kill this question, right? These are again 4 questions, okay? Now people, how to check the acidic strength? That is the point, yeah? See, if this ROH acts as the acid, that means it's going to donate H positive. When this ROH donates H positive, you get its conjugate base as RO negative, right? This is the conjugate base of this ROH, right? Similarly, what about the conjugate base of this RSH? When this RSH will leave H positive, you get the conjugate base as RS and the negative charge over here, right? Now compare the stability of these conjugate bases. Wherever conjugate base will be stable, there only acid is going to be stronger. Wherever conjugate base will be stable, there only the acid is going to be stronger. As simple as that. Now, since this RO negative, this is the conjugate base of this ROH, this RS negative, this is the conjugate base of this RSH, right? Okay. Now, wherein the conjugate base is more stable? Now, have a look. Right here, the negative charge is on oxygen, negative charge is on sulfur. Oxygen and sulfur, they belong to same group, right? And whenever we need to compare the stability of the charges on the elements which belong to the same group, at that time we consider the volume charge density. I told you a few minutes back, yeah? Okay. Now oxygen and sulfur. Sulfur has got more size. If sulfur has got more size, sulfur will be having less volume charge density. If sulfur has got less volume charge density, so stability is going to be simply more, right? I told you a few minutes back, stability is inversely proportional to volume charge density. So stability of RS negative is greater than that of RO negative. And whatever is going to be the stability order of these conjugate bases, same is going to be the acidic strength order of these acids, right? As simple as that, yeah? Okay. Let's move on to one more question then. See guys, I need to check which one among the following will be considered as maximum acidic, yeah? We need to check the acidic strength, right? See, when this CH4 loses H positive, there will be a negative charge on carbon. When this NH3 loses H positive, there will be a negative charge on this nitrogen. When this H2 loses H positive, there will be negative charge on this oxygen. When this HF loses H positive, there will be negative charge on this fluorine, right? So in their respective conjugate bases, we got negative charge on carbon, negative charge on nitrogen, negative charge on oxygen, negative charge on fluorine. Now this carbon, this nitrogen, this oxygen and this fluorine, they belong to same period, right? And whenever we need to compare the stability of the charges on the elements belonging to the same period, at that time, we consider the electronegativity, right? And we know negative charge is more stable on more electronegative element. So negative charge will be more stable on this fluorine, right? And whatever is going to be the stability order of the conjugate bases, same is going to be the acidic strength order of these acids. As simple as that, yeah? Okay. Wonderful. All right, let's move on and let's take this example over here. Right, have a look. When this molecule, this is ethane basically, when it loses H positive, there'll be negative charge on this carbon. Similarly, when this molecule loses H positive, there'll be negative charge, for example, on this carbon. Similarly, negative charge on this carbon, right? So where will be the negative charge more stable? Say, single bonded carbon, double bonded carbon, triple bonded carbon. We know triple bonded carbon is considered to be more stable. Triple bonded carbon is considered to be more electronegative. So I must say negative charge will be maximum stable on this carbon over here. And whatever is going to be the stability order of these charges, same is going to be the acidic strength order of these molecules over here, right? As simple as that, correct? Now there's a question for you. Can you let me know the answer of this fourth question? I'm waiting for your answers. Can you let me know the answer of the fourth question over here? We have got R single bond C, triple bond CH and NH3 over here. Can you let me know the acidic strength order of these two? What do you think? What do you think? Let me know first. What do you think? Well, people are saying 1, 2, then people are saying 2, 1. Who to believe? Okay, look here guys. When this molecule loses H positive, you'll be getting something like this, RC triple bond C, negative charge on this carbon, right? This is basically the conjugate base of this acid. Similarly, NH3, when it loses H positive, it becomes basically NH2 with a negative charge on this nitrogen over here, correct? Now people, if you see carbon and nitrogen, they belong to same period, right? If they belong to same period, you'll be talking in terms of electronegativity, right? And nitrogen is more electronegative than carbon. Normally we know that, yeah? Nitrogen is more electronegative than carbon. So negative charge should be more stable on this nitrogen. So this should be the stability order. So this should be the acidic strength order, right? But, have a look. This is sp hybridized carbon carrying the negative charge. And this over here is sp3 hybridized nitrogen carrying negative charge, right? Remember, electronegativity of sp hybridized carbon is more than that of electronegativity of sp3 hybridized nitrogen. Electronegativity of sp hybridized carbon is more than that of electronegativity of sp3 hybridized nitrogen. So this carbon over here is more electronegative, and we know negative charge is more stable on more electronegative element, right? So this is the stability of the negative charges. This is the stability of the conjugate bases, I must say. And whatever is going to be the stability order of the conjugate bases, same is going to be the acidic strength order, yeah? Let me know in the chat box if it is clear to everyone, yeah? Let me know fast with some thumbs ups. That's great. That's wonderful. That's great. That's wonderful. Okay. So let's move on then. Let's move on to a few more questions then. Yeah? Let's move on to a few more questions. So these 4 questions are also done and dusted right here. Yeah? Okay. Simple question, guys. Very, very simple question. Arrange the following according to the minus I power. Right? Arrange the following according to the minus I power. Okay? Right here you have got fluorine, which is attached with one carbon chain, OH attached with a carbon chain, and NH2, for example, attached with a carbon chain. I need to check which one is going to have more minus I power. As simple as that, right? Very simple question. See, fluorine is attached to the carbon chain, here oxygen is attached with the carbon chain, here nitrogen is attached with the carbon chain. Which one is more electronegative? Fluorine, oxygen, or nitrogen? Fluorine is more electronegative. So fluorine has got more tendency to drag the sigma bonded pair towards itself, right? Due to which fluorine will have maximum minus I power followed by OH followed by NH2. As simple as that, right? Now, what about the minus I power of these two groups? See guys, remember, minus I power of cationic group is always greater than minus I power of neutral group. Okay, this is the cationic group, this is the neutral group, and minus I power of cationic group is always greater than the minus I power of the neutral group, right? Okay. If I talk about the next case, see, this carbon is basically attached with the carbon chain. Similarly, this carbon is attached with the carbon chain. Similarly, this carbon is attached with the carbon chain. If I ask you, what is the hybridization of this carbon? You'll clearly say it's sp hybridization. What about the hybridization of this carbon? It's sp2. What about the hybridization of this carbon? sp3. If I ask you, which carbon has got the more s character among the all? This carbon has got the more s character. And remember, s character is directly proportional to electronegativity. So which carbon is more electronegative among the following? The first carbon is maximum electronegative among all these carbons, right? If it is maximum electronegative, that means it has got more tendency to drag the sigma electron pair towards itself, right? Okay, due to which it will be having maximum minus I power followed by this, as simple as that, right? Okay. Now, if you look at the last example over here, see, over here, this carbon is attached with the carbon chain. Similarly, this carbon is attached with the carbon chain. Similarly, this carbon is attached with the carbon chain, right? See, this CO bond, it will be polar absolutely. So there'll be negative charge on this oxygen, positive charge on this carbon. Similarly, carbon and nitrogen. Nitrogen is more electronegative, so nitrogen will get delta negative and carbon will get delta positive, right? Leave this case aside, okay? If I ask you, where is the magnitude of positive charge more? I mean, on which carbon among the two will be magnitude of positive charge more? See, in the first case, carbon is attached with oxygen, so the magnitude of positive charge is more for this carbon, right? If the magnitude of positive charge is more for this carbon, that means this carbon will have got more tendency to drag the bonded pair of electron towards itself. I mean, to drag the sigma electron pair towards itself. So this group is going to show maximum minus I power followed by this and the followed by last one, right? 1, 2, 3 is going to be the order. Let me know in the chat box if it is clear to everyone again, yeah? Let me know in the chat box. So basically, this C positive is more electron withdrawing than this C positive, than this carbon over here, right? Perfecto. Yes, Gyan, you can go for the NCRT, right? Okay, perfecto. The one who's having any sort of doubt, please drag the video a little back. It'll be automatically a replay for you, yeah? Perfecto. Let's move on to a few more examples then, yeah? Let's move on to a few more examples. Arrange the following according to minus I power. Arrange the following according to minus I power. You should clearly tell me now, these are the 4 questions again. You need to tell me which one among the two has got more minus I power. See guys, over here, this nitrogen has got the positive charge. This nitrogen again has got the positive charge. And in both the ones, nitrogen will be attached with the carbon chain, right? But people, you need to check the strength of the positive charge. You need to check the intensity of the positive charge. See guys, over here nitrogen is attached with 3 fluorine atoms, and right here nitrogen is attached with 3 hydrogen atoms. So I'll say the magnitude, the intensity of positive charge will be more on this nitrogen, so it will be more electron withdrawing. So minus I power of NF3 positive will be absolutely greater than that of minus I power of NH3 positive. Yeah, as simple as that, right? Absolutely right. Okay, now look at the next one. This one is done. Look at the next one. See, positive charge on nitrogen, positive charge on phosphorus, positive charge on arsenic, positive charge on antimony, right? Now, can you let me know, first of all the groups are cationic groups right now. Can you let me know what is going to be the minus I power of these groups? Yeah. Remember, positive charge on an electronegative element makes it more electronegative. Positive charge on an electronegative element makes it more electronegative, right? See, over here positive charge on nitrogen, positive charge on phosphorus, positive charge on arsenic, positive charge on antimony, right? Among nitrogen, phosphorus, As and Sb, which one is more electronegative? Nitrogen is more electronegative. So positive charge on nitrogen will make it further more electronegative, due to which this NH3 positive will become more electron withdrawing among the all, right? So this is going to be minus I. This is going to be minus I power order of these groups over here. Yeah? Wonderful. Perfect. Similarly, Oxygen having the positive charge, sulfur having the positive charge, Se having positive charge, T is having positive charge. Same reason you are going to give. Same reason you are going to give here also. No issues at all. Right? Same reason. Positive charge on oxygen will make it more electronegative than that of S positive, then that of Se positive, then that of Te positive. Due to which this O positive, it's going to drag the sigma electron density towards itself, due to which this OH2 positive group will be having more -I power than the rest. Yeah? Okay. Now people, in the last one, can you let me know the answer of the last question over here, the fourth question? Right? I'm waiting for your answers. Can you let me know the answer of the fourth question? I just want to see it exactly. What do you think about it? Yeah? What do you think? Which one will be having more -I power among the two? Which one is having more -I power among the two? Remember guys, remember, bond angle is directly proportional to what? Just a second guys, wait. We have got Nr3 positive, we have got NH3 positive. Okay, wait for a second. If I look at the structure, this is N positive, and over here you have got the bulky groups. N, this is R, and right here you have got N positive, and over here you have got 3 hydrogens attached. So if I use a normal logic, this R will show +I effect, right? It will increase the electron density towards this nitrogen, right? As per the normal logic is concerned. So positive charge will be least as per the normal logic over here. If positive charge is least over here, so I should say -I power of this NH3 positive should be greater than that of Nr3 positive, but the case is reverse. Okay? Remember, see, we have got 3 bulky groups over here. If we have got 3 bulky groups, I'll say they'll simply cause the steric repulsions, right? Due to which bond angle will increase. Remember, bond angle is directly proportional to the electronegativity of the atom, right? Remember, bond angle is directly proportional to electronegativity. If bond angle in this case will be more, that means electronegativity on this nitrogen will be more. If the electronegativity of this nitrogen is more, that means it will be having more tendency to drag the sigma electron density towards itself, due to which this Nr3 positive will be having more what? More -I power than that of NH3 positive. You can let me know in the chat box if it is clear to everyone or not. Just let me know. Just remember this thing. The bond angle is directly proportional to electronegativity. Right here, due to the repulsions, bond angle would have got increased, due to which electronegativity of nitrogen over here would have got increased, due to which it has got more tendency to attract the sigma bonded electrons towards itself, due to which it will be having more -I power than that of NH3 positive, right? As simple as that. Yeah? Perfect. Wonderful. Let's move on to one more question then, yeah? Let's move on to one more question. Arrange the following according to the stability order. A very simple question. A very simple question. I don't want you guys to use the hyperconjugation effect right now. Since I'm teaching you the inductive effect, I'm giving the questions on inductive effect. So I want you guys to solve these questions as per the inductive effect, not as per the hyperconjugation. Okay? Right? See guys. Over here you have got positive charge on this carbon, and this carbon is attached with 3 hydrogens, right? Positive charge on this carbon, on one side you have got CH3, on 2 sides you have got CH3, on 3 sides you have got CH3, right? CH3, your alkyl group, it shows +I effect, right? So all these CH3s, they'll try to push the sigma bonds, they'll try to push the sigma electron density towards this carbon. Similarly, over here you have got 2 CH3s, so they'll again push the electron density, sigma electron density towards that carbon. Similarly, right here, since over here, this carbon is not attached to any alkyl group, right? So can you let me know among which of the following positive charge would have got maximum nullified? Can you let me know among which of the following positive charge would have got maximum nullified, maximum compensated? Positive charge would have got maximum compensated in the last case, right? Due to which stability would have got increased, right? Yeah? Wherever charge is less in the molecule, whenever you see the charge is less on the molecule, at that time you can say that molecule is stable, right? So this one is maximum stable, followed by this one, right? Over here, positive charge would have got maximum compensated, right? Due to the presence of 3 alkyl groups, right? Okay, now people, negative charge on this carbon, negative charge on this carbon, negative charge on this carbon, right? Again, these CH3, these alkyl groups, they'll try to increase the sigma electron density towards this carbon. Similarly, what they are going to do the same thing. They are going to do the same thing. Similarly, this one is going to do the same thing, right? So these CH3 groups, I mean this group, and this group, what they are going to show, they are going to show plus I effect, due to which they'll increase the sigma electron density towards this carbon, due to which the magnitude of negative charge will increase, and if the magnitude of negative charge is increasing, that means the stability will be decreasing. So this one is going to be least stable, that means this one is maximum stable among all, right? As simple as that, yeah? Let me know in the chat box if it is clear to everyone. Let me know in the chat box if it is clear to every single guy, yeah? Perfect. Perfect, guys. Perfect. Let's move on to a few more then. Let's take a few more examples. Arrange the following according to the stability order. Arrange the following according to the stability order, right? So in the first question, you have got positive charge on this carbon, positive charge on this carbon, positive charge on this carbon, right? Have a look. You have got only on one side electron density is going to come, sigma electron density is going to come. On the three sides, electron density is going to come like this, sigma electron density. On just two sides, electron density is going to come, yeah, sigma electron density is going to come. You can clearly let me know, among which of the following the positive charge will be maximum compensated. The positive charge would have been maximum compensated in the second case. So second one is going to be more stable than that of third one, than that of first one, right? You need to see, first of all, wherever the charge is going to be less, there only stability is going to be more. As simple as that, yeah? Okay? Right? Right. Let me know fast in the chat box if it is clear to everyone. Okay, now talking about, you have got NO2 attached right here, you have got CN attached right here, you have got fluorine attached, right? Positive charge on this carbon, positive charge on this carbon, positive charge on this carbon. NO2 is more electron withdrawing than that of CN, than that of fluorine, right? If NO2 is more electron withdrawing, that means the intensity of positive charge on this carbon will be maximum, followed by this, followed by this. Wherever intensity of positive charge will be maximum, there only stability is going to be the minimum, right? So this is going to be the stability order, yeah? Let me know in the chat box if it is clear to everyone, right? Let me know in the chat box with the thumbs up if it is clear to everyone. Let me know fast. Exactly, it's going to be 3 to 1. 3 to 1 is going to be the order, stability order, right? Yeah? Perfecto. Let's move on and let's see some more questions. Okay. Right. Arrange the following according to their acidic strength, right? Remember, acidic strength, as you all must be knowing, acidic strength is directly proportional to minus effect. Acidic strength is directly proportional to minus effect, yeah? You all must be knowing about that, okay? See, in the first molecule, you have got 3 fluorines attached. In the second one, you have got 2 fluorines attached, right? And if you look at the first molecule, you have got the fluorine attached at the second carbon. You have got fluorine attached at the third carbon, right? So I'll say, in the first molecule, these 3 fluorines, what they are going to do, I'll say the effective minus I power in the first molecule will be more, and the effective minus I power of these 3 fluorine atoms, if it is more, that means what is going to happen? That means acidic strength in the first one is going to be more, right? Yeah? Or you can clearly say like this. See guys, you have got fluorine attached on the second carbon, you have got fluorine attached on the third carbon. You know, inductive effect, that is distance dependent, right? As we go far from the group, what happens with the inductive effect? Inductive effect, it decreases, right? Okay, we know it. Basically, we say inductive effect after the third carbon, we don't consider the inductive effect. We don't consider the charge present on the fourth carbon, right? You would have studied this, yeah? So clearly over here you can simply check, which one is going to be more acidic among the two. See, right here fluorine is on the second carbon, right here fluorine is on the third carbon. So fluorine is closer towards this group. Over here fluorine is a little far from this group, right? So fluorine over here is going to cause more minus I power. If fluorine over here is going to cause more minus I power, we know acidic strength is directly proportional to minus power, minus effect. So first one is going to be more acidic than that of second one, yeah? Right? Now what about the next one? As I told you, acidic strength is directly proportional to minus effects, right? See, If I talk about this carbon, this carbon, this carbon and this carbon, right? So from here, hydrogen will leave as H positive, so that will be negative charge on this oxygen. Right here, hydrogen will leave as H positive, negative charge on this oxygen. Hydrogen will leave as H positive, negative charge on this oxygen. And similarly, hydrogen will leave as H positive, negative charge on this oxygen. Yeah? Okay. Now we will check it out. This carbon is maximum electronegative because of more angle strain, because of more strain in this molecule. Yeah? This one is maximum electronegative. If this carbon is maximum electronegative, can I say negative charge is more stable? Or you can say like this. See, this carbon is more electronegative, right? If this carbon is more electronegative, can I say it will decrease the negative charge on this oxygen right here? Okay, or you can say this carbon is more electron withdrawing than that of this, than that of this, than that of this, right? Okay, yes. So you can clearly say right here, negative charge is more stable, or you can clearly say this ring over here, it is going to show minus I effect, the maximum minus I effect, followed by this ring, followed by this ring, followed by this ring, right? Okay, now you can clearly say the acidic strength is going to follow this order, right? Because I told you your acidic strength, that is directly proportional to minus effect, right? I told you acidic strength is directly proportional to minus effect, yeah? Wherever minus effect is more, there only acidic strength is more. Minus effect is more in the first case, so in the first case, acidic strength is going to be more. You can let me know in the chat box if it is clear to everyone, yeah? Let me know fast. Let me know fast with some thumbs up so that I can give you a few more questions. Exactly, Darshini, because of strain. Yeah. Strain is the reason. Perfect, guys. Let's move on and talk about a few more examples. Okay, some important examples, guys. Some important examples. Okay, see. Arrange the following according to their acidic strength, yeah? See, first of all, when hydrogen leaves as H positive, there will be negative charge on this carbon, so you get something as CF3, negative charge on this carbon. When hydrogen leaves as H positive from here, you get something as CCl3, negative charge on this carbon, right? Okay. Now, basically, this is the conjugate base of this acid. Similarly, this is the conjugate base of this acid. Wherever conjugate base is stable, there only acid is going to be stronger, right? Now, check among the two. Wherein the conjugate base is more stable? Wherein the conjugate base is more stable? Well, people are saying 1, then 2. No way, no way. This conjugate base is more stable than that of first one. What is the reason? What is the reason? See, guys. Over here you have got negative charge on the carbon. Over here you have got negative charge on fluorine. I mean negative charge on this carbon. See, this carbon is attached with fluorine. Does fluorine have any vacant orbitals? Does fluorine have any vacant orbitals? Fluorine does not have any vacant orbitals. Its octet is complete, right? Okay. Now people, this chlorine, it has got some vacant d orbitals. If this chlorine has got some vacant d orbitals, can I say this negative charge with a lone pair, it can form some back bonding over here? Due to this back bonding, this conjugate base is more stable. And if this conjugate base is more stable, that means this acid is going to be stronger than that of this acid, right? Yeah, as simple as that. Be careful with all this. Yeah. Now you can clearly let me know the answer of the second question. See, if I take hydrogen out as H positive, there will be negative charge on this carbon. If I take hydrogen out as H positive, negative charge on this carbon, right? Since this oxygen, it does not have any vacant orbital. This sulfur, it has got vacant d orbitals, right? It has got vacant orbitals. Okay, due to the presence of vacant orbitals, there can be the possibility of back bonding. And if there is back bonding in this conjugate base, so that stabilizes basically this conjugate base, due to which this acid is going to be stronger than that of this acid, right? As simple as that, right? Be careful with all this. Be careful with all this. Just let me know in the chat box if it's clear. Let me know fast with some thumbs ups, yeah? So that I can move on to the next question. Let me know fast. Let me know fast, yeah? Perfect, guys. Wonderful. Darshini, just wait for it. Wait for it. Wait for it. Okay. All right. Let's take a look on the next one. Arrange the following according to their basic strength, right? I need to arrange these two as per their basic strength. Okay, look here guys. This nitrogen over here is sp3 hybridized, yeah, sp3. What about this nitrogen? What about this nitrogen? It is sp2 hybridized, right? So you can clearly say this nitrogen has got more S character. If this nitrogen has got more S character, that means this nitrogen is more electronegative. If this nitrogen is more electronegative, this nitrogen is not going to donate this lone pair of electron easily as compared to this nitrogen. Wherever among the two, nitrogen is going to donate its lone pair easily, that molecule only is going to be more basic. So which one can donate lone pair easily? The first one, right? The first one can donate lone pair easily, and that one which can donate lone pair easily, that's going to be more basic, right? So one is going to be more basic than that of second one, yeah? As simple as that, right? Okay, now check the basic strength among the two, okay? Which one is more basic? Let me know fast. You can clearly tell me. You can clearly tell me. You can clearly tell me which one is going to be more basic among the two. Fast. First, you have got chlorine attached at this position, fluorine attached at this position, right? Fluorine shows more minus I. If fluorine shows more minus I, there will be less availability of this lone pair to get donated, right? That means there is more availability of this lone pair to get donated. So wherever the availability of lone pair to get donated is more, there only you can say the basic strength is more. So first one is more basic than the second one, yeah? Okay. Okay, let me know fast if it's clear to everyone. Similarly, on the basis of hybridization, you can decide this one as well. On the basis of hybridization of nitrogen, you can decide the availability of lone pair, right? You can decide the availability of lone pair, wherein lone pair is going to be more available, right? Wherein the lone pair is going to be more available, there only the basic strength will be more, right? Yeah, and lone pair is more available over here because this nitrogen is sp3 hybridized. If it is sp3 hybridized, it has got least S character, less electronegative. That means this nitrogen has got more tendency to donate this lone pair of electrons. So this one is going to be more basic than that of second one, than that of first one, right? 3 to 1 is going to be the order. Yeah, absolutely. Perfecto. Now comes one more. Which of the following molecules shows resonance? Which of the following molecules shows resonance? You need to tell me which one among the following will show resonance among all, okay? Now, first of all, if you look at the conjugation, this is pi, just a second, what did I do? This is pi, this is sigma, right? Over here, you should have the vacant p orbital with a positive charge, right? If this kind of conjugation is possible, this is what we call as pi, sigma, vacant orbital conjugation. Wherever you see pi sigma vacant p orbital conjugation or simply pi sigma vacant orbital conjugation, there only resonance can happen, right? Okay. Now people, this phosphorus over here, it has got the vacant orbital. Which vacant orbital it has? It has got vacant d orbital basically, right? So the conjugation right here is pi sigma vacant orbital, right? This phosphorus, it has got the vacant d orbital, right? So over here, pi sigma vacant orbital conjugation. So resonance is possible, right? Similarly, pi sigma vacant orbital, right? So conjugation is possible, that means resonance is possible, right? In the next one, you have got again pi, this is sigma. This boron, if you check its octet right now, in its octet you'll be only having 6 electrons, so there is one empty p orbital, right? So pi sigma empty orbital, so conjugation, that means resonance, yeah? What about the last one? In the last one, you have got just pi, this is sigma. Over here, you do not have any vacant p orbital. You do not have any vacant orbital. If you do not have any vacant orbital, so there'll be no resonance possible in the fourth case, right? Let me know in the chat box if it is clear to everyone. So 1, 2, and 3, they'll show the resonance, and the last one is not going to show any sort of resonance. See, if I talk about this boron, its octet is already completed. It has got no vacant orbital. If it has no vacant orbital, that means it's not going to show any sort of conjugation right here. So no resonance is going to happen in the fourth case, yeah? As simple as that, yeah? Perfecto. Let's move on to one more then, yeah? Let's move on to one more question. Which of the following molecules shows resonance? Okay, you need to check which one of the following will show resonance. First of all, this is your pi bond, this is sigma. Over here you should have the vacant orbital. But does nitrogen have vacant p orbital over here or some vacant orbital? It does not have any vacant orbital. Its octet is already completed over here. It is making 4 bonds, yeah? Okay, so since there is no vacant orbital, no resonance, yeah? What about the second one? This is pi, this is sigma. In phosphorus, you have got vacant d orbital, right? So pi, sigma, vacant orbital, conjugation, resonance, right? Okay. Right. Now, what about the next one? There is negative charge on this carbon, right? Positive charge on this carbon, free radical on this carbon. This carbon over here is sp2 hybridized. Even this is sp2 hybridized. Even this is sp2 hybridized. See guys, this negative charge is actually right now in sp2 hybridized orbital. This positive charge is again in sp2 and this free radical is in sp2. What is resonance basically? Resonance is the overlap of the parallel p orbitals basically, right? So can you let me know, will the resonance happen? Will these molecules show resonance? No way. See, you have got one empty p orbital right here, perpendicular to the plane, but this negative charge, okay, it is present in sp2. Okay, so basically there is the angle 90 degree between the pure p orbital of this carbon and this sp2 hybrid orbital. So resonance is not possible in this one. For the resonance to happen, there should be two parallel p orbitals present, right? Over here, you do not have two parallel p orbitals present. Similarly, you do not have two parallel p orbitals. You do not have two parallel p orbitals present, right? So resonance not possible, resonance not possible in this case, resonance not possible in this case as well, yeah? Okay, I'm sure it's clear to everyone. I'm directly moving on to one more, yeah? Okay, give the correct stability order of the following resonating structures. Yes, we'll be going into the into the isomerism questions as well. Just wait for it. Yeah. Let me know fast. Let me know fast what should be the order. Give the correct stability order of the following resonating structures. What do you think? Give the correct stability order of the following resonating structures. It's very, very simple, guys. Yeah, very simple. First of all, in the first molecule, you do not have any charge separation. So first one is going to be maximum stable, followed by second and third. Now count the bonds. Count these sigma bonds. Count the total covalent bonds. 1, 2, 3, 4, 5, 6, and 7. 7 covalent bonds. 1, 2, 3, 4, 5, 6, 7, 8. 8 covalent bonds. Wherever the number of covalent bonds is more, their only stability is more. So third is more stable than that of second, right? So 1, 3, 2 is going to be the order, stability order of these molecules. As simple as that, yeah? Wonderful. Let's move on to one more question then. Okay, basically these are two more questions. Give the correct order of the following resonating structures. We need to give the correct order of the following resonating structures, yeah? Okay. So people, first thing, over here you have got 1, 2, 3, 4 covalent bonds. 1, 2, 3, 4 covalent bonds. 1, 2, 3, only 3 covalent bonds. Wherever covalent bonds will be least, their only stability will be least. So third one is the minimum stable among all, right? Now among 1 and 2, say guys, nitrogen has got the positive charge. Over here nitrogen has got the positive charge, right? Now one more nitrogen has got the negative charge. Over here carbon has got the negative charge. Now I'm not going to compare the stability on this nitrogen because in both the molecules, nitrogen carries the positive charge. Now talk the stability of the negative charge. Negative charge is more stable on more electronegative element. So nitrogen is more stable. So 1 is going to be maximum stable, followed by 2, followed by 3, right? As simple as that. Right? Let me know fast in the chat box. Let me know fast in the chat box if it is clear to every single guy, yeah? Let me know fast. Let me know fast. Okay, wonderful. If you look at the next molecule, have a look. In this first molecule, you do not have any charge separation. In the second molecule, you have got the charge separation over here. In the third molecule, you actually have the charge separation. Okay. Well, let me tell you, wherever there will be no charge separation, wherever there'll be no charge on the molecule, that's going to be maximum stable. So 1 is maximum stable, right? 1 is maximum stable. Now among 2 and 3, wherever charge separation will be less, stability is going to be more. So 2 is more stable than 3 because over here charge separation is less than that of this one, right? Wherever charge separation will be less, their only stability will be more, right? Less charge separation means less potential energy. Less potential energy means more stability, yeah? right? Rajam, simple, you count the covalent bonds. Wherever covalent bonds will be more, there only stability will be more. That's it, yeah? Okay, perfecto. Let's move on to these two molecules. Which among the following is more stable? Which among the following is more stable, right? Again, two more questions. People, you can solve it. You can let me know its answer. See guys, understand. If I compare the first two molecules, the lone pair which is present on this nitrogen, it's in conjugation with this pi bond and this pi bond, right? It is in conjugation with this one as well as in this one, right? Okay, so one lone pair is simultaneously in conjugation with two pi bonds over here. So this is the case of cross conjugation basically. This is the case of cross conjugation if you remember. What about this one? This is the normal case of extended conjugation, right? This is the normal case of extended conjugation. I mean the linear conjugation, not the extended one exactly. To be more precise, it is the normal case of linear conjugation. This is the case of cross conjugation. Well, the extent of resonance in cross conjugation is definitely going to be less, and wherever extent of resonance will be less, stability is going to be less. So which one will be more stable? First one will be more stable than that of second one. Because in the second one, you have got cross conjugation. In the cross conjugation, we know extent of resonance is less, and wherever extent of resonance will be less, there only stability will be less. So one is going to be more stable than that of second one, yeah? What about the next one? What about the next one? See, you have got pi, sigma pi. So one type of conjugation over here. Similarly, one more type of conjugation, right? So the same pi bond is in conjugation with two pi bonds at the same time. So this is the case of cross conjugation again. And this is again the case of linear conjugation. This is the case of linear conjugation, right? Okay. This is the case of linear conjugation. And we know extent of resonance in cross conjugation is always less. If the extent of resonance and cross conjugation is less, stability of it is going to be less. So stability of this one is going to be more than that of first one, yeah? 2 is more stable than that of first, right? I'm sure it's clear to everyone. Perfect. Okay, let's move on to a few more examples, yeah? Okay, arrange the following in the stability order. We need to arrange the following in the stability order. People, before solving this question, let me give you one clear-cut concept over here. Remember, we know negative charge is more stable on more electronegative element, right? Negative charge is more stable on more electronegative element. If I'll be having negative charge on oxygen and if I'll be having negative charge on carbon, where will be the negative charge more stable? On oxygen, negative charge is more stable. Remember, negative charge carrying capacity of one oxygen atom is more than the negative charge carrying capacity of 10 carbon atoms. Negative charge carrying capacity of one oxygen atom is more than the negative charge carrying capacity of 10 carbon atoms, right? Okay, now people understand. I need to check the stability, I guess, yeah? Arrange the following in the stability order, okay? Which one is going to be the most stable? People, if you look at this molecule, right? Can I say over here we have got the conjugation, right? This negative charge can come here, this negative charge can come here, right? This pi bond will be coming here in the form of negative charge. So negative charge is splitting on two oxygen atoms, right? And negative charge carrying capacity of oxygen is more than that of negative charge carrying capacity of 10 carbon atoms. So D is going to be the maximum stable because negative charge is being splitted on two carbon atoms. D is maximum stable. So I've got nothing to do with this D, right? Now apart from that, which all molecules contain oxygen? See, this molecule contains oxygen, this molecule contains oxygen, right? See, this molecule is containing oxygen, so it can show resonance. This negative charge can come on this oxygen, right? Yeah. Even this has got oxygen, right? Carrying a negative charge, so this negative charge can participate in the resonance, right? So if oxygen atoms in both the molecules are same, then after that I'll be talking in terms of extent of resonance. In which of the following, B and E, wherein the extent of resonance is more? In case of E, extent of resonance is more. Splitting of this negative charge is more. If the splitting of negative charge in E is more, that means E is more stable, then comes your B. Right? This one is gone, this one is gone. Now we are left with this one, and this one, right? Now people, negative charge is there on carbon, and over here due to resonance, negative charge can come on this nitrogen, right? And right here negative charge on this carbon. Negative charge on more electronegative element is more stable, so then comes your C. Now among your F and A, wherein negative charge is more stable, you will simply see the extent of resonance. In F, extent of resonance is more. In A, extent of resonance is less. So F comes first, then at the end comes your A. This is going to be the order of the stabilities, right? Let me know in the chat box if it is clear to everyone so that we can move on to the next one. Yeah? Let me know in the chat box first if it is clear to every single guy so that we can move on to the next one. Yeah? Let me know fast. Let me know fast. Yeah? Let me know fast. Gayatri, not yet. I'll be letting you know about that. Okay. Pride FPSTD. Why? Why E should not be more stable? Okay, so I'm moving on to one more question then, right? Let's try to solve this question. Compare the bond lengths, right? You need to compare the bond lengths. I mean, these selected bond lengths. This bond length, right? This bond length and this bond length. Basically, you need to compare the bond lengths between nitrogen and carbon. You need to compare the bond lengths between nitrogen and carbon, okay? People understand. If you look at the first molecule, since there is no conjugation at all, so nitrogen and carbon, they are present with the help of a single bond. They are attached with the help of a single bond, right? Since over here we do not have any sort of conjugation, so between nitrogen and carbon you have got a double bond, right? Okay. If you look at the third case, there is a lone pair on nitrogen, so it can participate in resonance, due to which this N and C, they'll get the partial double bond character. So due to resonance, this N and C is getting the partial double bond character. Over here again, due to resonance, this N and C will be getting the partial double bond character, right? Okay, right? So where will be the bond length maximum? Bond length will be maximum in the first case. Bond length will be maximum in the first case, right? Where will be the bond length minimum? See, you have got a perfect double bond, a proper double bond between nitrogen and carbon. So second is going to have minimum bond length, right? Now among these two, where is the bond length minimum? Wherever among these two extent of resonance is more, wherever extent of resonance is more, there only the partial double bond character will be more, and wherever the partial double bond character between nitrogen and carbon will be more, there only bond length will be less. So 4 is going to have less bond length than that of 3, right? So 3 comes first, 3 comes first, then comes your 4, then comes your 2, yeah? Okay? 1, 3, 4, 2 is going to be the order, right? 1 is going to have the maximum bond length, right? Followed by third, followed by fourth, followed by 2. Absolutely, guys. I'm sure it's clear to everyone, right? Okay, so, okay, one more question, one more nice question, guys. Compare the acidic strength of the hydrogens, okay? You need to check which hydrogen is more acidic. You need to check which hydrogen is more acidic. How do we check this? See, let's assume hydrogen leaves as H positive, there will be negative charge on this sulfur. If hydrogen leaves as H positive, negative charge on this oxygen. If hydrogen leaves as H positive, negative charge on this oxygen. Hydrogen leaves as H positive, negative charge on this nitrogen, right? So first of all, you need to check where among the following negative charge is more stable. Wherever negative charge will be more stable, there only H is going to be maximum acidic, right? So this negative charge is in conjugation with this pi bond like this. Yeah, so basically this negative charge is spread between two oxygen atoms, and you got to know a few minutes back the negative charge carrying capacity of oxygen is far greater than the negative charge carrying capacity of carbons, right? Okay, so people, you can simply say fourth one is the maximum acidic, right? Because negative charge is maximum stable in the fourth case, so your fourth hydrogen is going to be maximum acidic, right? Now, talking about negative charge on this sulfur and negative charge on this oxygen, do they belong to same period or same group? They belong to same group, and along the group, we need to check on the basis of what? Volume charge density. Which one has got more size? Oxygen and sulfur. Sulfur has more size. If sulfur has more size, that means sulfur has less volume charge density. If sulfur has less volume charge density, right? So it's going to be negative charge is going to be more stable. If negative charge will be more stable, then that means this hydrogen is going to be more acidic than that of second one, and at the end you'll be having the first one. So 4, 3, 2, 1 is going to be the order of the acidic hydrogens among the two. Yeah? See, 4 then 3, right? Now in 2 and 1, in 2 and 1. Negative charge on oxygen, negative charge on nitrogen, right? Negative charge on oxygen, negative charge on nitrogen. Oxygen and nitrogen, they belong to same period. If they belong to same period, you'll be comparing the stability of negative charge on the basis of what? Electronegativity. Since oxygen is more electronegative, so negative charge is more stable on oxygen. That means this hydrogen is going to be more acidic than that of this hydrogen, right? So 4, 3, 2, 1 is going to be the order, right? Walaikum salam, Miss Kashmir. Yes, Rajam, we have got COO negative. Basically, it is COH at the 4th position. Yes. Okay. I'm sure it's clear to everyone. So you got to know how to identify the acidic hydrogens as well. Arrange the following in mesomeric power. People, you can solve these questions as well. These are very, very simple questions. Yeah. Let's see how these questions are to be solved. Understand properly how these questions will be solved. We need to arrange them on the basis of their mesomeric effect, yeah? Right? Mesomeric power. First of all, see, if I need to identify which one has got the more mesomeric power, I'll be making a perfectly conjugated system over here. I'll be attaching these groups with the perfectly conjugated system, right? I'm attaching these groups with the perfectly conjugated system like this. Okay. Now, people, first of all, this O with a negative charge, right? It's in conjugation with this conjugate system, due to which it will take part in resonance. Even this lone pair will take part in resonance. Lone pair on this oxygen will take part in resonance. Lone pair on this nitrogen will take part in resonance, right? Due to which partial polarity gets developed between the group and the conjugate system, right? So basically, this group, is it donating the pair of electron? Yes, it's donating the pair of electrons, right? Okay, basically this group, it is increasing the pi electron density in the conjugate system. So this group is basically showing plus M effect, right? Similarly, this group is increasing the pi electron density in the conjugate system. So this group is again showing plus M effect. Same for this, same for this. Now I need to check wherein plus M effect is more. Which group shows more plus M effect? I need to check which group shows more plus M effect. Say guys. Negative charge on oxygen, negative charge on nitrogen, negative charge on this oxygen, negative charge on this nitrogen over here, yeah? I mean, lone pair on this, yeah? Now, first of all, remember, plus M power of the anionic group is always greater than plus M power of the neutral group. Remember this. That means plus M power of 1 and 2 is going to be greater than that of plus M power of 3 and 4. Now, in 1 and 2, which one can donate this electron pair easily, right? Which one can donate this electron pair easily for resonance? See, this oxygen is more electronegative, so it cannot donate this electron pair for resonance with the same ease as that of this nitrogen. So 2 is going to show more plus M power, followed by the first. Now, among these two, lone pair on oxygen, lone pair on nitrogen. Lone pair will be more available on this nitrogen, right? Okay, I mean the fourth one is going to be 2, 1, then comes your 4, then comes your 3. This is the order of plus M power among the following, right? 2, 1, 3, 4. Yeah? I'm sure it's clear to everyone. Now, if you talk about the next one, see, you have got lone pair on this oxygen, right? Lone pair on this sulfur as well, lone pair on this silurium as well, right? Now, we will see. If you need to check, first of all, you should know, since this lone pair is going to participate in the resonance when the groups are attached with the conjugated systems, right? So all these three groups, they are going to show plus M power. Now, which one shows more plus M power? See, over here, you'll be having a conjugate system right here like this, yeah? So this resonance is going to be between, it's going to be 2p overlap. Right here, it's going to be between 2p, 3p overlap. Right here, it's going to be between 2p, 4p overlap, right? 2p overlap is maximum. 2p overlap is maximum. That means this this electron pair, it is more available for resonance. If it is more available for resonance, you can clearly say 1 is going to show maximum plus I power, followed by 2, followed by 3, right? This is the plus M power of the 3. Yeah, 1, 2, 3 is going to be the order. Just let me know in the chat box if it is clear, so that I can move on to the next one. Yeah, exactly. They'll show plus M power. Yes. Okay, let's move on to one more question then. Arrange the following in the stability order. you need to compare the stability order, right? Now, how to solve this question? Understand. First of all, arrange the following in the stability order. Okay, you have got negative charge on this carbon, negative charge on this carbon, negative charge on this carbon, and negative charge on this carbon, right? If you need to compare the stability order, right, you need to see the effects which are being operated by these groups over here. See, this NH2, it is present at the meta position. Sorry, it's present at the para position, right? So NH2, it shows plus M effect. Since this NH2 present at the meta position, it will show minus I effect, right? This OH at the para position will show plus M effect because oxygen has got the lone pair, it can participate in resonance, right? This PR3, it's going to show what? Which effect it's going to show? It is going to show minus M effect, right? It's going to show minus M effect, correct? Yeah? Okay. Now people, stability of negative charge is directly proportional to minus effect. Stability of negative charge is directly proportional to minus effect. Stability of negative charge is directly proportional to minus effect. And remember, minus M dominates over minus H and minus H dominates over minus I, right? So which one is going to be maximum stable? So fourth one is going to be maximum stable, followed by, this shows minus, right? So followed by the second one. Now among 2 and 3, among 2 and 3, this is NH2, this is OH. Which one has got more plus M power? Which one has got more plus M power? Is it going to be NH2 or is it going to be OH? Can you let me know in the chat box? I just want to see it. Among 1 and 3, which one has got the more plus M power? See, after 4, 2 comes. That's clear, right? Now in 1 and 3. Absolutely, guys, you all are right. So the order is going to be, wait, where has it gone? Just a second, guys. Okay, it's here. So the order is going to be 4, 4, 2, then comes your 3, then comes your 1, right? OH has got more plus M power than that of NH2, right? It's going to be 4, 2, 3, 1, yeah? I'm moving on to one more question. You can clearly let me know answer of this question, but I'm sure you are going to make a mistake once, right? Give it a try, let me know the answer. Arrange the following as per the Ka values. Basically, you are supposed to check the acidic strength order. You're supposed to check the acidic strength order. Remember, first of all, I'm selecting the reference. OH is everywhere, right? I'm selecting the reference. I've selected the reference over here. Yeah? I've selected the reference over here. Now, remember, acidic strength is directly proportional to minus effect. And we know minus M dominates over minus H and minus H dominates over minus I. This is something which you should know. See guys, you have got nitro group attached right here. It is going to show minus M effect, right? CN is going to show minus M effect, right? Talking about this fluorine and chlorine. Remember, whenever you get parachlorophenol, this is parafluorophenol, right? First of all, halogens, they show two effects, inductive effect as well as mesomeric effect, right? But normally we say for halogens, inductive effect dominates over mesomeric effect, yeah? Yeah? But remember, in this case, electron withdrawing nature of this chlorine is more than that of electron withdrawing nature of this chlorine is more than that of electron withdrawing effect of what? Fluorine. Okay. Now, first of all, since these two are operating minus M and minus M of NO2 is more, so first one is maximum acidic followed by second one. Now, among these two, which one is more electron withdrawing? This Cl is more electron withdrawing. I want you guys to remember it. So 4 comes first, then comes your 3. So 1, 2, 4, 3 is going to be the order of it. Yeah. Exactly, guys, right? So let's move on to one more. Arrange the following in the order of Kb values. Okay, we are supposed to arrange them on the basis of their Kb values, right? Basically, we are going to arrange them on the basis of their basic strengths, right? Now let's arrange them on the basis of their basic strengths. I'm sure it's clear. See, CH3, right? First of all, let's try to identify the reference. This O negative everywhere is the reference. You can see it, yeah? Now this CH3 is present at the meta position. If CH3 is present at the meta position, it's not going to operate hyperconjugation effect over here. It's simply going to operate plus I effect, right? This NO2 and CHO, right? NO2 and CHO, they are adjacent. So steric SIR effect is going to happen over here, steric inhibition of resonance, due to which this nitro is not going to show minus M effect over here. This nitro is not going to show minus M effect, and I'm not going to take minus I effect of nitrogen as well, of NO2 as well, because NO2 with respect to this O negative is present at 1, 2, 3, 4, fourth carbon atom, and after third carbon atom, we say the inductive effect vanishes. So it is as good as there is no NO2 over here, right? This CHO, it's present at the meta position. This CHO, which effect is going to operate over here? It's going to operate simply minus I effect, yeah? What about this NO2? At meta position, minus I, right? What about this chlorine? What about this chlorine? Chlorine is right now present at what? Chlorine is present at the para position. So I'm not going to consider its inductive effect. I'm going to consider its plus M effect, right? Okay. Now we need to check what? Arrange the following in the order of their Kb values. We need to check their basic strength, right? Basic strength. Okay. So basically we need to see the intensity of negative charge on this oxygen, right? So remember, basic strength is directly proportional to plus effects, okay? And remember, plus M dominates over plus H, and plus H dominates over plus I for the basic strength, right? So which one is showing plus M? Fourth one is showing plus M, right? Fourth one is showing plus M, right? Fourth one is gone. Then which one is showing plus effect? This one is showing plus effect. So after that, 1 comes. Now among 2 and 3, which one is showing less minus I? This one is showing less minus I, CHO. So 2 comes, then after 2, you'll be having 3. So 4, 1, 2, 3 is going to be the order of it, right? 4, 1, 2, 3 is going to be the order of the basic strength among the 4. Yeah? I'm sure it's clear to everyone. Right? Right. Let's move on to what just happened. Okay, now talking about this one, talking about this case, guys. It's already, the answer is given. I don't know what happened to this one. So finally, let's solve it. First of all, you need to identify the common group. This is the common group which I'm identifying right here. Okay. First of all, you would have seen this molecule. This is what we call as guanidine, right? It is considered to be maximum basic. It is considered to be maximum basic. So 1 is maximum basic. Leave the first case, right? Over here you have got NH2 which shows plus M effect. So basically remember your guanidine, it's considered as highly basic. So 1 is maximum basic. Now among these 3, since this OH it shows plus M, this CH3 it shows simply plus I right here, and this CN it shows minus M, correct? Now you can clearly see the order. I told you the basic strength is directly proportional to plus effect, and plus M dominates over everyone. Plus M dominates over everyone. So after your 1, 2 comes, then after 2, plus I and minus M, 3 comes, then after 3, your 4 comes. Simple 1, 2, 3, 4 is going to be the order, yeah? 1, 2, 3, 4 is going to be the order, right? I'm sure it's clear to everyone. Identify the molecules, whether they are aromatic, anti-aromatic, and non-aromatic, right? We are given with some 4 molecules. We need to check whether these are aromatic, anti-aromatic, or non-aromatic, right? What are the conditions for the molecule to be anti-aromatic and aromatic, right? First of all, for the molecule to be aromatic and anti-aromatic, what are the conditions? For the molecule to be aromatic, the molecule should be cyclic. In case of anti-aromatic, again the molecule should be cyclic, right? Okay. Every atom in the ring should be sp2 hybridized. Every atom in the ring should be sp2 hybridized. The number of pi electrons involved in the cyclic conjugation should be equal to 4n plus 2 pi, right? As per Huckel's rule, it should be simply 4n pi electrons should be present in the cyclic conjugation, right? Okay. Now you can see. First of all, every atom right here is sp2 hybridized. This sulfur is also sp2 because it's one of the lone pair. It's participating in the resonance. So I do not have to consider this lone pair for the hybridization. It's going to be 1, 2, and 3, right? Steric number is 3. So it's going to be sp2, right? Okay. Right. Now we will understand. See, this is sp2, and sp2, correct? First of all, it's cyclic, right? Every atom is sp2. Now, how many electrons are involved in the complete cyclic conjugation? 2 to 4 to 6. So we have got 6 pi electrons involved in complete cyclic conjugation. In the second one, you can see every atom is sp2 over here, right? The circumferential atoms are sp2 hybridized. Okay, it is cyclic at the same time, yeah? And at the same time, how many pi electrons do we have involved in the cyclic conjugation? 2, 4, 6, 8, 8 and 10, right? Okay, so 10 pi electrons involved in the complete cyclic conjugation. 2, 4, 6, 8 and 10, yeah? Now what about this one? Since this carbon is sp3, so it cannot be aromatic, it's non-aromatic. Okay, since this carbon is sp3, it's again non-aromatic, right? This is non-aromatic, this is non-aromatic. Now check these two, 6 pi electrons, put the value of n as 1, so 4 plus 2, 6 pi, so this is aromatic, right? Okay, we have got 10 pi electrons, put the value of n as 2, so 4 2s are 8, no, okay, put the value of n as 2 over here, 4 2s are 8 plus 10, so it is again aromatic, right? So aromatic, non-aromatic, non-aromatic. So I got these molecules over here, right? This aromatic, non-aromatic and non-aromatic, right? Yeah. Similarly, if I give you 4 more examples, you can clearly let me know, which molecule is aromatic and which molecule is non-aromatic and anti-aromatic at the same time. See, first of all, every carbon right here is sp2, okay? So how many electrons are involved in complete cyclic conjugation? 4 pi electrons. Over here, this negative charge, it's in conjugation. This one is also in conjugation. So 2, 4, 6. 6 pi electrons as per Huckel's rule. See, over here, this is sp3 hybridized. So this is clearly your non-aromatic. Okay. sp3, non-aromatic, right? Okay. Remember, aromatic plus anti-aromatic. Aromatic plus anti-aromatic makes it anti-aromatic, right? Now, people, if you look at this molecule, I'm going to draw this molecule like this so that it'll be slightly little more clear to you. I'm drawing the same molecule like this, no issues, right? See, this ring is aromatic, this ring is anti-aromatic, right? See, in the first ring, this ring which I'm talking about, you have got 6 pi electrons involved in the complete cyclic conjugation. In this ring, you have got 2 to 4 pi electrons involved in complete cyclic conjugation. So this first one ring is aromatic, the second one is anti-aromatic. Aromatic plus anti-aromatic makes it anti-aromatic. So this molecule overall as the whole is anti-aromatic, yeah? Okay. So 4 pi electrons means anti-aromatic, right? 6 pi means aromatic, this non-aromatic, right? Everything is done. I'm sure it's clear to everyone. Anti-aromatic, aromatic, right? This non-aromatic, non-aromatic, and the last one is anti-aromatic, right? Okay, as simple as that. Yeah? So basically you remember one thing from now onwards. Aromatic plus aromatic makes the molecule aromatic, right? Aromatic plus anti-aromatic makes the molecule overall as anti-aromatic, right? Just remember these two things. This is enough. Perfect, guys. Wonderful. Okay. Arrange the following according to their stability order. Well, people, we have already solved these two questions. Right here, the same two questions which we solved on the base of inductive effect in the beginning. Same questions we are solving on the base of hyperconjugation, right? So simple, if you need to compare the stability, right here, if I talk about this carbon, and this carbon, right? The other carbon which is attached to this carbon over here, okay, that's what I call as alpha carbon. Over here you have got, this is the alpha carbon. Right here we do not have any alpha carbon. And the hydrogens which are attached with the alpha carbons are called as alpha hydrogens. So you have got 0 alpha hydrogen in this case, you have got 3 alpha hydrogens in this case, and you have got 2, 3, 5. You have got 5 alpha hydrogens in this case. So third one is stabilized by maximum alpha hydrogens. Wherever alpha hydrogen will be maximum, there only stability will be maximum, right? Similarly, this is your alpha carbon and this is alpha hydrogen. This is 1 alpha hydrogen, these are 2 more alpha hydrogens, right? These are 3 alpha hydrogens, these are 2 more, these are 2 more. So alpha hydrogens are maximum in third case, so stable maximum followed by 2 followed by 1, yeah? Okay, as simple as that, right? I'm sure it's clear to everyone. Arrange the following according to the Ka order. Arrange the following according to the acidic strength order. You need to arrange the following as per their acidic strength is concerned, right? See guys, first of all, you select your reference. This COH is a reference, this is a reference, right? You're selecting the reference over here. We know acidic strength is directly proportional to minus effect. Acidic strength is directly proportional to minus effect, right? CH3 over here operates plus hyperconjugation effect. It is right now at meta position, so it will be operating plus inductive effect, right? CCl3, it will be operating minus hyperconjugation effect. CBr3 will be operating minus hyperconjugation effect. This CCl3, it will be simply operating what? It will be simply operating minus I, right? Because it's present at the meta position, okay? And we know minus M dominates over minus H and minus H dominates over minus I, right? Now you can clearly let me know the order of the acidic strengths, okay? Now first of all, see. Minus H, minus H. Remember, CBr3, it shows more minus H than that of CCl3, right? So fourth one is going to be maximum acidic followed by third one. So cancel them out, yeah? Now this one shows minus I, so fifth comes after that, right? Now among first and second, plus H and plus I. So I'll give preference to second and then I'll be giving preference to the first one, right? This is the order. This is the acidic strength order, right? Okay, 4, 3, 5, 2, 1. 4, 3, 5, 2, 1 is going to be the acidic strength order. I'm sure it's clear to everyone, right? Vaishnavi, which question are you talking about? Wait, I'll check the previous question. Did we do any sort of mistake in the previous question? I don't remember exactly. So, this was the question, I guess, right? Okay, where you are saying exactly? Where did I say? What did I say in the last question? So, this is the alpha hydrogen, right? Okay, this is one alpha hydrogen. These are two alpha hydrogens, correct? This is two alpha hydrogens and three alpha hydrogens, right? Okay, so over here you have got 1, 2 and 3 alpha hydrogens. Right here you have got just 1 alpha hydrogen. Right here you have got 7 alpha hydrogens, right? So 7 will be maximum stable, followed by 2, followed by this one, right? First wala part 3. Okay, this is the alpha carbon, so 2 alpha hydrogens, right? So you have got 2 alpha hydrogens right here, correct? So what's wrong in it? See, you have got 2 alpha hydrogens right here. Over here, you have got how many alpha hydrogens? 3 alpha hydrogens. Right here, no alpha hydrogens, right? So 2 is going to be maximum stable, followed by 3, followed by 1. Did I say opposite of it in the last one? Okay. All right. No issues. My bad if I say opposite of this one. Okay, this question is done. 4, 3, 5, 2, 1 is going to be the order. This is something which we have done, right? Okay, arrange the following according to their Ka value. Wait, you just change the question. It's not Ka, it's Kb order. Arrange them on the basis of their basic strength order. Right? Basic strength order. First of all, select your reference. This is the reference. Okay. Now, remember your basic strength, it is directly proportional to plus effect. And remember, plus M dominates over plus H and plus H dominates over plus I. Right? The CH3 is at para position, so it will show plus H effect. Right? CCl3 at para position minus H effect. Right? CH3 at para position, it will show plus I effect. Right? And CCl3 at meta position. See, this at meta position, so plus I. This is again at meta position, so which effect it's going to show? It's going to show minus I effect, right? Okay, now check. The question is done and dusted. Okay. So first of all, we have got only one molecule in which plus H operates. So first one is going to be maximum basic, followed by the third one, which shows plus effect, right? Now among second and fourth, which shows less minus effect. Fourth one, then comes your second one. 1, 3, 4, 2 is going to be the basic strength order, yeah? Right? Right? Let me know fast. Miss Kashmir says, sir, one of me too. Surely, why not? I stay in Kashmir only. Yeah? Okay, wonderful. Clear to everyone? Should I be moving on to the next one? Yeah? Okay, let's move on to the next one then, right? Let's move on. 1, 3, I said the same order, right? 1, 3, 4, 2. 1, 3, 4 and 2. Yeah, exactly. Okay, identify the following as chain or position isomers, right? Identify the following as chain or position isomers. The first one, see, I'm going to give you a simple rule by means of which you can check chain isomers and position isomers, okay? Let me give you a simple rule. First of all, there is something called as CS rule, where C stands for number of carbon atoms, simply I'm writing number of atoms in the parent chain, number of atoms in the parent chain, and S stands for the number of substituents starting from carbon, starting with carbon, okay? Now, first of all, I'm going to get the value of CS for this molecule, and then I'm going to get the value of CS for this molecule. If you look at the parent chain, 1, 2, 3, 4, 5, 6. So C value is 6. Number of carbon atoms in the parent chain is 6. Now, how many substituents do we have? We have got only one substituent, and that substituent is starting from the carbon. So S value is 1. So 61 is the value of CS for the molecule number 1, right? Similarly, molecule number 2. How many carbon atoms in the parent chain? 1, 2, 3, 4, 5, 6. So C value is 6. S, we have got one substituent starting with carbon, so 61. Whenever CS value comes out to be same, whenever CS value for two molecules comes out to be same, right? CS value comes out to be same, we call those molecules are the position isomers. So these two are basically position isomers. When the CS value does not come out to be same, we call them as chain isomers, right? So first one, this one and this one, CS value is same, so these are going to be your position isomers, okay? Now what about these two? Understand properly. We start the numbering from the bridgehead carbon 1, 2, 3, 4, 5, 6, 7, 8. So how many carbon atoms in the parent chain? 8. How many substituents do we have? One substituent, two substituents. Are these two substituents starting with carbon? Yes. So 82 is the value of CS in the first case. Similarly, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? C value is 10. Is there any substituent starting with carbon? No. So CS value is 100. Is the CS value coming out to be same or different? Different. So these are going to be what? These are going to be chain isomers, right? As simple as that. So first two were position isomers, second two, these were chain isomers, right? Yeah. So till now we have done around 82 questions, is that? People, simple remember one thing, when the value of CS for two molecules comes out to be same, we call those molecules to be position isomers, and when the value of CS comes out to be different, we call them as a chain isomers. And what is C basically? C stands for the number of atoms in the parent chain, S stands for the number of substituents which start with carbon, as simple as that, yeah? Okay? Perfecto. Let's move on to a few more examples, right? Now you are going to arrange, you are going to check these molecules, are these position or chain, right? Let's have a look. Let's see again how this sort of question is solved, right? First of all, I'm going to give the numbering like this: 1, 2, 3, 4, 5, 6, 7, 8. How many carbon atoms are there in the parent chain? 8 carbon atoms. So C value is 8. What is the S value? Is there any substituent starting with carbon? There is no substituent. So CS value is 80. What about CS value over here? Again, give the numbering: 1, 2, 3, 4, 5, 6, 7, 8. So 8 carbon atoms in the parent chain. Is there any substituent starting with carbon? No. Again, CS value is 80. Since CS value is coming out to be same, so both the ones are going to be position isomers, right? They're going to be position isomers. As simple as that, right? Okay. Now people, let's talk about the second one. 1, 2, 3. The CS value is going to be 33. 1, 2, 3. Number of atoms in the parent chain is 3. And 3 substituents starting with carbon. So 33 is the CS value. 1, 2, 3, 4. It is 42. 42 is the CS value. CS value is not coming out to be same. So these are going to be your chain isomers, right? As simple as that. Let me know in the chat box if it's clear to everyone. Let me know in the chat box if it's clear to everyone fast. Let me know in the chat box with the thumbs ups if it is clear to everyone. Perfecto. Wonderful, guys. Okay, now draw the tautomers of the following. We are going to draw the tautomers of the following, right? We have got some 4 questions, right? And you can clearly draw their tautomers. How do we draw the tautomers? Okay, first of all, this is the reference which I'll be talking about. Just a second. let me fix the carbonyl group as the reference. This is the reference. Similarly, this is the reference, this is the reference, this is the reference. That carbon which is attached, that carbon which will be attached with this C double bond O, okay? That carbon which is attached with this C double bond O is what I call as alpha carbon. So this is alpha carbon, this is alpha carbon, this is alpha carbon, and this is alpha carbon, right? Similarly with the phenyl, you'll be having the first carbon of phenyl as the alpha carbon, yeah? Now for the tautomerism to happen, this alpha carbon should be sp3 and there should be alpha hydrogen attached with this alpha carbon as well, okay? Similarly with the alpha carbon, this alpha carbon should be sp3 and there should be hydrogen attached with this alpha carbon, okay? Similarly, alpha carbon should be sp3, then only tautomerism is going to happen. So we will understand. This is C double bond O, this is the alpha carbon, but this alpha carbon is sp2, so over here tautomerism is not going to happen because this alpha carbon should be sp3, yeah? Right? Okay, similarly, if you talk about the second case, see, this is C double bond O, this is your alpha carbon, this is sp3, right? This is sp3. So tautomerization is going to happen in this case, yeah? So what is going to be, how you are going to draw its tautomer? See, first of all, this alpha carbon is sp3, it has got alpha hydrogens as well. So how you will be drawing its tautomer? Simply just drag this double bond over here, take one of the H positive and attach with this oxygen, so you get something as CH2, and over here you get double bond, this is O, this is hydrogen, and with this carbon you have got hydrogen. This is the tautomer of this molecule, yeah? Right? Okay, if you look at the next case, see, C double bond O, carbonyl, right? This is your alpha carbon, but this is sp2 hybridized, so no tautomerism at all, yeah? Similarly, in the last case, no tautomerism at all. No, wait. In the last case, tautomerism is going to happen. See, this is alpha carbon, this is alpha carbon. The first carbon of this phenyl ring is alpha carbon, but that is sp2, so it is this carbon, the carbon of the phenyl ring is not going to participate in the tautomerism. So over here, this carbon is going to participate in the tautomerism. Over here, you have got one hydrogen, right? Just drag this bond over here. Just remove this H positive and attach with this oxygen. So you get something as PH, single bond C. This is O, this is H, and you get a double bond over here in between. And right here, you get one cyclohexene ring like this, okay? So these two are tautomers of each other, correct? Yeah? As simple as that. Right? Okay. Draw the most stable and the least stable forms of the following. Draw the most stable and least stable forms of the following, right? How do we solve this question? First of all, I would draw the Sawhorse projection of this molecule. If I'll draw the Sawhorse projection of this molecule about this alpha and beta carbon, so this alpha and beta carbon I'll be representing by a straight line, yeah, alpha beta carbon. You have got chlorine attached with this carbon and two hydrogens. Let's see, this is your chlorine, right? This is chlorine, and this is, for example, one of the hydrogen, this is one more hydrogen, correct? If I talk about this beta carbon, and on this beta carbon, for example, this is chlorine, right? You have got two hydrogens at well, this is one hydrogen, this is one hydrogen. This is the Sawhorse projection of this molecule, right? So from Sawhorse, what I'll be doing, I'll be drawing the Newman's projection, correct? So how do I draw the Newman's projection? I look at this carbon-carbon bond along this way. This is my axis of sighting, okay? So if I look about this double bond in this way, I can only see this carbon, and that carbon which I can see, I'll be representing that by a single bond, by a dot. This dot is the carbon, which is what I can see. With this carbon, you have two hydrogens attached like this. These are two hydrogens attached, and in the downward direction, you have got chlorine attached. This is the carbon which you cannot see, and that carbon which you cannot see will be represented by a circle. And with this circle, you have got chlorine attached at the top, like this. You have got hydrogen attached over here at this position. You have got hydrogen attached at this position. It is one of the Newman forms of this, yeah? Okay. Now we will understand. What is the dihedral angle over here? Dihedral angle is 60 degree. So this is the example of the staggered form. This is the example of the staggered form. Whenever in a molecule the dihedral angle is 60, we call that form as the staggered form, right? Now people, if I'll rotate the circle 60 degree clockwise, if I rotate the circle 60 degree clockwise, can I say from staggered I'll be getting eclipsed form? From staggered I'll be getting eclipsed form. In the staggered form, dihedral angle is 60 degree. In the eclipsed form, dihedral angle is 0 degree. And remember, staggered is stable than that of eclipsed. So this form, this is the staggered form, which is considered to be more stable. And if you rotate this circle about 60-degree clockwise, you'll be getting what? Eclipsed form, which is considered as less stable. Yeah. Okay. Right. Let me know fast if it's clear to everyone. Yeah. Let me know fast if it's clear to everyone. So if you remember, your staggered form, it's considered to be generally more stable than that of eclipsed form, right? Because of the less torsional and van der Waals strains, right? Perfecto, guys. I'll be giving you a few more examples, okay? See, this is your staggered form, right? This is your staggered form. So did we have 2 chlorines attached in the molecule? I think we made a mistake. I think we made a mistake in this question, yeah? I think we made a mistake in this question because I forgot to attach chlorine on this with the circle. I think so. Still, let me try it once more. See, if you try to make the sawhorse projection, so about this alpha and beta, I'll be drawing a single line. This is a single line, right? You've got 2 hydrogens attached. Let's say this is chlorine. This is one of the hydrogen. This is one of the hydrogen, right? If I talk about this beta carbon, this is the beta carbon. You've got 1 chlorine attached over here, and you have got, for example, one hydrogen over here and 1 hydrogen over here, for example, right? Now, if I try to draw the Newman's projection from this, you'll be looking at this bond along this way. So this is the carbon which you can see. The carbon which you can see is represented by a circle. This is chlorine attached right here. This is hydrogen attached right here. This is hydrogen attached right here. This is the carbon which you cannot see. I'll be drawing a circle instead of it, right? You've got one of the chlorine attached over here. You've got one of the hydrogen attached over here, one of the hydrogen attached over here, right? Since the dihedral angle is 60, so it is what I call a staggered form, right? Dihedral angle is 60, which is what we call a staggered form. And in the dihedral angle, if the bulky groups are of the opposite sides, we call it as the NT form, and NT form is the most stable in the staggered form, right? Now, similarly, I'm going to rotate this circle 60-degree clockwise. You'll be getting something as this form, which is called as fully eclipsed form, and staggered form is definitely more stable than that of fully eclipsed form, right? I think my answer was okay only. Yeah? Okay. I thought I didn't write this Cl at the top. I thought I wrote some H over here. Yeah? Yes, Pranav. Tautomerism only will happen when there will be when your alpha carbon is going to be sp3 hybridized, there'll be alpha hydrogens, right? Otherwise, there'll be the possibility of the space tautomerism. That's one more case. Okay, whenever you see the tautomerism in any system apart from your diad and triad system, that's something which we call as space tautomerism. That's something which I have taught already in NEET Elite channel. Okay, perfect. Draw the most stable and the least stable forms of the following. Okay, we have got this molecule. Okay, I'm going to draw the sawhorse representation of this molecule about this alpha and beta. So this is a straight line which I'm drawing like this. Okay, this is basically your alpha carbon, and with this alpha carbon you have got pH attached. This is pH, for example, right? And you have got one CH3 group as well. So for example, this is your CH3 group, and this is one more hydrogen which is attached with this carbon. Similarly, if I consider this beta carbon, with this beta carbon you have got phenyl group pH attached and 2 hydrogens. This is one hydrogen, this one hydrogen, correct? This is the sawhorse representation. Now people, if I look at this C-C bond, right, about this way, you can only see this carbon, and the carbon which you can see, that's something which I represent by a dot, and with this dot you have got pH attached downwards, right? You have got CH3 attached almost at an angle of 120, and this one more hydrogen. Okay, this is the carbon which you cannot see, and that carbon which you cannot see is represented by a circle. So you have got pH at the top like this. You have got hydrogen over here. You have got hydrogen over here as well. So people, again the dihedral angle over here is 60 degree. So it is again the staggered form. And in the staggered form, which form is it in the staggered form? See, the bulky group are on the opposite side. So this is the NT form, right? Which is considered to be very, very stable. So this is the most stable form. This is the most stable form, correct? Now similarly, if you rotate the circle 180 degree clockwise, you'll be getting 2 phenyl groups on the same side. So at that time, after the rotation of the circle by 180 degree clockwise, you'll be getting fully eclipsed form, which is considered to be very, very unstable. So let me show you exactly. This is your staggered, and when I rotate the circle 180 degree clockwise, you'll be getting eclipsed form, right? Staggered is more stable than that of eclipse. So this is the more stable form, this is the least stable form, right? Okay. I'm sure it's clear to everyone, right? Right. Draw the most stable form of the following by using GOC effect. So what is this GOC effect all about? See guys, a very simple thing. First of all, about this carbon and nitrogen, I'll be drawing the Newman's projection, right? So this is the nitrogen. This is going to be my site from where I'll be seeing along this way. Nitrogen is something which I can see. So this is the nitrogen which I can see. And on this nitrogen, I've got a lone pair. This is the lone pair. And you have got 2 hydrogens attached with this as well. So 2 hydrogens. So this is the carbon which I cannot see when my site is going to be from nitrogen to carbon, right? So carbon is something which I cannot see. So that's something which I'll be representing by a circle. You have got 2 hydrogens and 1 CH3, right? You have got 2 hydrogens and 1 CH3, right? First of all, as per the GOC effect is concerned, see, at this beta carbon, which one is the bulky group attached with this beta carbon? CH3 is the bulky group attached with this beta carbon. So I'm going to attach this bulky group at the GOC position, with respect to this lone pair. With respect to this lone pair, GOC position is either this or this. So you are going to place bulky group at this position or at this position. Choice is all yours. For example, I'm placing it right here, CH3, okay? So what all things are left? 2 hydrogens, one of the hydrogen is here and one of the hydrogen is here, right? This is the most stable form, right? Due to GOC effect, this is the most stable form over here. This is the most stable form, yeah? Right? Let me make a few more examples so that you get the clear-cut idea of all this. Okay, we are going to draw the most stable form of this. Again, I'll be using a GOC effect. I'll be seeing the molecule along this way. So oxygen is something which you can see. Oxygen is something which you can see, right? And towards this oxygen, you have got 2 lone pairs and 1 CH3. Let's say this is 1 lone pair. This is 1 more lone pair, right? And this is CH3. This is the oxygen which you can see, correct? And this carbon is the beta carbon, right? This carbon you cannot see. I'm drawing it, I'm representing it by a circle like this. Okay, now at this beta carbon, you have got a bulky group CH3. Now, as per GOC effect, you are going to place this bulky group at the GOC position with respect to lone pair. Now, GOC position is either this or this one, right? Now, if I place CH3 over here, there will be repulsions between 2 bulky groups, so it's better to place CH3 over here, right? So CH3 is placed, now 2 hydrogens are left. This is 1 hydrogen and this is 1 more hydrogen. This is the most stable form which you'll be getting right here, yeah? Okay, most stable form which you'll be getting right here, correct? Right? Wonderful. Now people, let's take a few more examples. Which of the following can show geometrical isomerism, right? We are given with some molecules and I'm supposed to check which of the following can show geometrical isomerism, right? Okay, let's try to understand. In order to show geometrical isomerism, 3 conditions must be satisfied, okay? If you select any 2 centers in a molecule, the rotation should be hindered. The rotation should be hindered between the 2 atoms which you are selecting in the molecule, right? Now, these are the 2 bonds attached with this carbon right here, for example. These are the 2 more bonds, for example, attached with this carbon, right? First condition is the rotation between these 2 atoms, between the 2 selected atoms should be hindered, point number 1. Point number 2, these 4 bonds, they should be either present on the same plane or the plane containing these 2 bonds and the plane containing these 2 bonds, those 2 planes should be parallel to each other, right? This is the second condition. The third condition is with respect to this center, 2 different groups should be attached, and with respect to this center, 2 different groups should be attached. For example, AB, right? Only this molecule can show geometrical isomerism which satisfies these 3 conditions. Yeah? Okay, let's check it out. Let's have a look. First of all, if I select these 2 carbon atoms, since the rotation is hindered between these 2 carbon atoms, right? But you have got 2 same atoms attached with this carbon, 2 same atoms attached with this carbon. Atoms attached with this carbon must have been different, so this is not going to show geometrical isomerism, right? Okay. if you select this atom and this atom, right? These are the two centers which I've selected, right? This is one of the hydrogen over here. This is one more hydrogen over here, correct? This is sp3, this is sp3. So the plane containing these two bonds and the plane containing these two bonds, those planes will be parallel to each other, point number one. Point number two, rotation is restricted between these two atoms, right? And you have got two different groups attached with this carbon, right? This is CH3, this hydrogen, this CH3. So this one is going to show your geometrical isomerism, right? Second one will show the geometrical isomerism. Okay, what about the next one? What about the next one? If you select this carbon and this carbon, first of all, rotation is restricted, point number one. You cannot rotate it because the ring is going to break then, yeah? Okay, now, this is hydrogen, correct? Rotation is restricted. sp3, sp3. The plane containing these two bonds and the plane containing these two bonds, both the planes will be parallel, correct? Now, what all groups are attached with this carbon? This hydrogen and this group. Similarly, this hydrogen and this group. So two different groups are attached with the carbon. So this is going to show geometrical isomerism, right? Yeah? Okay. Now, if you look at the next case, select this carbon and this carbon. You have got two same hydrogens attached with this carbon. So it's not going to show geometrical isomerism, right? Okay. If you select this nitrogen and this carbon, on this nitrogen you will be having a lone pair as well, and lone pair is considered as a group, right? So you have got hydrogen with this as well. So first of all, this nitrogen is sp3, this carbon is sp3. So the plane containing these two bonds and the plane containing this lone pair and a bond, both the planes are parallel to each other. Rotation is restricted between this nitrogen and carbon, right? And the groups attached with the nitrogen are different, and the groups attached with this carbon are also different. So it's going to show GI, yeah? Right? What about the next one? Is it going to show GI? Yes, it's going to show GI. Just check about this carbon and this carbon, right? It's going to show GI. Okay, it's going to show GI. This one is not going to show GI because if you look at this carbon and this carbon, right here, I'm sorry, right here two same methyl groups are attached, so it's not going to show GI. What about the last one? It is going to show GI, correct? This is hydrogen, for example. This is hydrogen, for example. It is going to show GI. Yeah? So which all showed GI? Second one showed GI, third one showed, this one showed, and the last one showed the GI, geometrical isomerism, right? I'm sure it's again clear to everyone, yeah? Priyanka, I'm almost done. Okay, there are, I guess, few more questions. No, the session is over, right? The session is over. I'm sure you would have enjoyed the session. People, do let me know in the comment box once the session ends, whether you liked it or not. Whether you want me to come regularly on this channel, you can let me know that in the comment box, yeah? Do let me know that, right? So because of that only, I'll get to know whether you like the session or not. And people, at the same time, if you want to see the actual sessions which we have been taking on YouTube in physics, chemistry and maths, I highly suggest you guys to come to JEE Enthuse, where JEE Enthuse is the name of the channel on YouTube, where me, Shimon Sir and Shrey Sir, we take sessions every day for the JEE people, right? Okay, so do check it out, check the channel out, right? And the ones who have not liked the video yet, please do like the video, share the video with your friends, and do not forget to subscribe to the channel as well, right? Yes, and people, with this, I'll take the leave right now. It was nice meeting you all, right? Do let me know in the comment box whether you liked it or not. Till then, okay, once checking your comments, I'll see whether you want me back on this channel or not, okay? So I'll hopefully see you guys soon. Till then, you take care. Bye-bye. God bless you all and love you all. Take care, guys. Bye.